Welcome everyone to this section. We'll be discussing Module 6 of EC402 Nanoelectronics. The topic of today's discussion is HBTs, heterojunction bipolar transistors. So we all know that the normal application of a transistor is in switching and amplification. So when transistors are used as amplifiers, a high value of beta will result in good amplification, right? So the desirable property for a BJT is to have a high value of amplification factor beta up to the largest frequency possible. Now the maximum operating frequencies for these BJT devices will depend upon several design parameters like the geometrical dimension, doping levels of emitter, doping levels of base and collector regions, etc. So we know that to have a high value of beta, both alpha and gamma should be close to unity. You can see the equations here where gamma is equal to beta plus 1, beta is equal to alpha by 1 minus alpha. So when alpha, which is the current gain through the base, and gamma, which is the injection efficiency factor of the emitter, is close to unity, we get a high value for beta. So in order to make alpha and gamma close to unity and to get a high value of beta, in the fabrication, what we should do is the doping of emitter region should be made higher than that of the base. Okay. So when the doping concentration increases, that results in a reduction in energy gap of semiconductors. And finally, we can observe a noticeable reduction in carrier injection from emitter region to base region. So it is seen that there is a some around 14% band gap reduction when the doping level reaches to 10 raised to 20 per centimeter cube. So in order to get a high value of beta, what we are doing is we are doping the emitter high. So when we dope the emitter section higher compared to base, the energy gap of semiconductor decreases and there will be a reduction in carrier injection. So when William Shockley designed these transistors, he also found that when the emitter is fabricated using a different band gap material like a wide band gap material, this amount of injected carriers from the base region to the emitter region can be reduced. Then the overall injection efficiency of the emitter can be improved, which means we can improve the beta factor. We know that beta depends upon alpha and gamma. So in order to make gamma near to unity, what he found is that when we use different materials for emitter and base, we can achieve this functionality. And when we use the normal BJTs are called homojunction BJTs because we use the same material in emitter, base and collector. But when we use a different material at emitter and base, then that becomes a heterostructure or heterojunction bipolar transistors or HBTs, right? So HBT is just an improvement of BJT. It can handle signals of very high frequency, some around several hundred gigahertz. Now, what is the main difference? Main difference between a BJT and HBT is the use of different semiconductors for emitter and base region in order to create a heterojunction. So in a conventional BJT or in a homojunction BJT, we use same type of materials at the emitter and base region, but in a heterojunction BJT, we use different semiconductor materials. So generally we use high band gap or wide band gap semiconductor materials at the emitter side and narrow band gap materials at the base side. So that becomes a heterojunction. And what is the advantage which we are getting? We get a high amplification factor, beta. Now you can see from this diagram that this is the band structure for homojunction and heterojunction. Figure A shows for homojunction BJT and figure B shows for heterojunction BJT. Now what is seen is that the band gap at the emitter side and the base side are almost same in case of homojunction BJT, and the barrier injection of electrons from emitter to base EVN is also is equal to the EVP, the injection of holes. Okay, but in case of a heterojunction BJT, you can see that since we are making the emitter with a wide band gap material compared to the base, the band gap at the emitter side is much larger when compared to the band gap at the base side, and also the barrier injection of electrons from emitter to base EVN is lower than that of the corresponding holes EVP. EVN is lesser than that of EVP, which means if the barrier height decreases, that means electrons can easily get injected from emitter to base side. So there is a notable increment in the beta factor, which means we get high amplification for the heterojunction bipolar transistor. Now, we already told how it is constructed. Now, the beta factor, it is also proportional to the ratio between the doping concentrations of emitter and base region, and it also depends upon the factor e raised to minus delta Eg by kBt, where delta Eg is the energy difference between the value of wide band gap of emitter and narrow band gap of base, and kBt is a Boltzmann's constant. So by varying the doping and delta Eg, we can vary the beta factor, right? Now HBTs can be fabricated with heavily doped base region and with very low value for base region and for electron transit times to the base. Okay, so now we'll see what are the improvements which we can do to this HBT. So suppose if the doping of the emitter is reduced, then that results in a smaller parasitic capacitance associated to the emitter base junction. Now, this reduction in the parasitic capacitance at the emitter base junction and the reduction of the base resistance, which we discussed just now, these two factors, the reduction in base resistance and the reduction of the parasitic capacitance of the emitter base junction, will be essential when we use HBTs at higher frequencies. Okay, when we use HBTs at higher frequencies, there should be a reduction at the base resistance and a reduction at the parasitic capacitance of the emitter base junction. So in order to get a reduction in the parasitic capacitance of the emitter base junction, the doping at the emitter should be somewhat reduced. Right. Now, another improvement in HBT is by grading the composition of base layer so that the band gap energy of the material is gradually reduced throughout the base. Okay, so look into this diagram. The diagram A shows HBTs with graded base region and diagram B shows a double HBT, a different construction, which I'll come to it later. So a graded base HBT, we can see that the base region, the base layer is graded, means the band gap decreases from one end to another end, right? So this grading causes an electric field that can accelerate electrons traveling through base region, which in turn reduces the transit time, and we can use HBTs at higher frequencies. So that is one method, one improvement. Another improvement is by fabricating a wide bandgap material at the collector side. Means the collector section also we are using a wide bandgap material. Already we are using a wide bandgap material at the emitter side. Now if we make a wide bandgap material at the collector side, then that structure will be called a double HBT or DHBT. So the breakdown voltage of the base collector junction can be increased, and this circuit, the transistors, the circuits made with DHBTs, they can be easily used in the design of ICs because the emitter and collector terminals can be interchanged. Okay, so that is the another improvement in HBT, which is called DHBT, double heterojunction bipolar transistor. Now we'll see some features of HBT. The base length of HBT should be about 50 nanometer, and doping concentration should be in the range of 10 raised to 19 per centimeter cube. Normally, HBTs are manufactured from group 3 to 5 semiconductors because of their high mobility, and 3 to 5 semiconductor based HBTs can be easily integrated into the ICs that include electronic and optoelectronic devices. That is one advantage. And suppose if we are using aluminum gallium arsenide heterojunction HBTs, we can use such HBTs up to a frequencies of approximately 100 gigahertz. Now, if you use a different material like indium gallium arsenide, indium aluminum arsenide, or a combination of indium gallium arsenide and indium phosphide based HBTs, it will allow us to use HBTs to a much higher operating frequency, some around 200 gigahertz with low noise. So generally, HBTs based on silicon technology are developed, which make use of different silicon compounds as wide bandgap materials. And HBTs made from silicon germanium alloys can also be fabricated. Then we call it silicon germanium based HBTs. In that case, how it is constructed is the silicon emitter region will be followed by a silicon germanium base region, so that the band gap of that base region, silicon germanium base region, will be smaller than that of the silicon emitter region. And we know that the band gap of silicon is 1.12 eV and that of germanium is 0.66 eV. Right. So silicon germanium based HBTs can also be fabricated. Now, this band gap energy difference allows the doping of base region with relatively high concentrations, thus extending the operating frequency to values comparable to the 3,5 compounds. So a gradual base region can be grown by changing the value of the X in the compound, like GX SI1 minus X. Suppose if GX SI1 minus X is the compound, by varying the value of X, we can make a gradation in the doping values of the base region, and that results in a high built-in electric field, which will further result in a reduced transit time as they travel through the base, and we can operate such uh, HBTs at higher frequencies. So the main purpose is to reduce the transit time and use it at a higher frequency. So these are the changes or improvements which we can do in a HBT. Now, when we compare HBT and a MOSFET, HBTs have higher power dissipation when compared to MOSFETs. So these are the main features of a heterojunction bipolar transistor. So I hope you understood the working of HBT and some of its main features. Thank you.